So my name is Zach Shwirya-Conti, and I'm a Turing Research Fellow at the Alan Turing Institute here in London. And I would also like to introduce my colleague and co-organizer of this seminar series, Andrea Pizzoferato, who is a visiting academic here at the Turing. And for those of you who are not familiar with the Turing, and I'm sure you've heard me say this 1,000 times now, the Turing is UK's National Institute for Data Science and AI. And on a side note, if any of you are interested in sharing your work in one of these seminars, please, of course, do get in touch with either Andrea or myself. We'd be happy to find a slot. Questions may be asked towards the end, or if our speaker today is okay with it, maybe also throughout the presentation. So without further ado, I'll ask my colleague Andrea to introduce our speaker for today, and thank you all.
Okay, thank you, Zach. So our speaker today is Jan, who started his academic journey by attending undergraduate courses at the Department of Information Engineering, Automation Mathematics at the Slovak University of Technology. At the same institution, he completed his PhD on learning-based approaches towards solutions of model predictive control. He then continued his postdoctoral training, first at the QA Leuven, and then at Pacific Northwest National Laboratory. Here, while advancing his career as a data scientist, he contributed to Climate Change, a nonprofit working at the intersection of climate change and machine learning. He now leads as a principal investigator a team of research scientists working on differentiable programming methods for modeling and control of dynamical systems with applications in energy. He's also a lead software developer of the Neuromancer library in PyTorch for solving constraint optimizations, physics-informed machine learning, and optimal control problems. Today, Jan is going to share with us his work at the Neuromancer library. And without further ado, Jan, the floor is yours. Thanks again for joining us today.
Thank you very much, Andrea and Zach, for the invitation. It's a real pleasure. I will be talking about our software toolkit that we started and developed 4 years ago as a small prototype, and really intention was to have productivity tool for our internal team at PNNL. But we quickly realized that there is demand for these capabilities in a broader communities, and we went open source, and we received a lot of wonderful feedback. So that's a joint work with Aaron Tour, James Cook, Madeline Shapiro, Rahul Birmival, and Drgona, who are contributing to the library. And our motivation as researchers at the National Lab is to develop some tools to support heterogeneous applications in the space of Department of Energy in the United States, which is our primary sponsor of our work. And there are heterogeneous applications from basic energy sciences, from material science, power systems, or building energy systems that are heterogeneous in physics and also heterogeneous in scale, but they have something in common. And that very often we have high fidelity simulators to do the forward modeling of these systems, because that's necessary for any area of decision-making and scientific discovery. However, there is the challenge when taking these high fidelity simulators for closing the loop for optimization, design, and control. These software tools are not typically differentiable. They cannot be just plug and play in existing optimization toolkits. And that has been the bottleneck for doing the autonomous experimentation or optimal control at scale. So there is an emerging solution in the community that we believe is an answer to that, and that's scientific machine learning or physics-informed machine learning, where you systematically combine some reduced order physics or certain properties you want to satisfy in your data-driven model with modern AI methods like deep neural networks. So we are very excited about these new emerging opportunities, and we really see it as a landscape of modeling tools that we typically have at our disposal when we are approaching specific problem at hand. Depending on the requirements, you may go from fully model-based models that people from engineering are familiar with, MATLAB, Simulink, or Modelica. That's everything engineered. The disadvantage of those is, as I mentioned, they are complicated in terms of development time. It takes months typically to design and tune them, and they are also expensive to run computationally. On the other hand, like in the black box space with purely data-driven neural networks, you have no guarantees on stability, on constraint satisfaction, or on conservation laws or structural assumptions about your system. So we are really interested in here in the middle, in traditionally what has been called gray box modeling, and the scientific machine learning or physics information learning. You can really think of it as a new fancy way of doing gray box modeling at scale and with more expressivity. And topics that are falling in this category are neural differential equations with domain priors, like universal differential equations, graph neural networks, and many others. So we are interested in this space, and then we want to use these models to solve a range of problems. When you are dealing with operation research type problems, optimal design or optimal control, we are typically solving constraint optimization problems in real time, where in traditional way, you know your objective functions and constraints, and you parse them in specific solver formulation. So depending on the form, you can use quadratic solvers or some mixed integer programming solvers. But there is no learning here historically. And the same with differential equations. Historically, you need to know your right-hand side of a differential equation, and you use appropriate solver to integrate this continuous time model. But what we see lately is that more and more physics, so like constraint satisfaction and principles of differential equations and solvers are being used in machine learning, and vice versa. More machine learning is being used to either warm start optimization solvers or tune some of their parameters, like step sizes in differential equation solvers. So there is a nice convergence of these two originally separate domains, engineering and computer science. But because of this historic separation, there have been also development of the tools in silos. We are familiar with a lot of constraint optimization frameworks. If you are coming from controls and operation and research background, you have been using PyMod, Jump, Gecko, or CVXPy, or Casadi for nonlinear optimal control, which are algebraic and differentiable modeling languages that allow you to formulate models in symbolic way on a high level of abstractions, and then parse that high level of abstractions into specific problem formulation to call solver like interior point or active set methods. And something similar you have in differential equation libraries, whether they are general purpose, like in Julia or MATLAB or SciPy, or more domain specific for power system in PETSI-Tau, or really like domain specific NW Chem libraries for molecular dynamics. And again, historically, there have been no machine learning in this. And when we see the revolution what deep learning brought, I would argue that one of the contributing factors is that their software tools are superior in user friendliness and scalability. That is one of the reasons that where you see machine learning these days in every single scientific and engineering applications, and there is a lot of demand for that. Because it's so easy to train neural networks using PyTorch or TensorFlow these days that any grad student can do it within a week on any project. And what we see these days is development of the new libraries like JAX or scientific machine learning ecosystems in Julia that are combining constraint optimization, differential equations, and control in the ecosystem of machine learning. So it's typically called like differential programming that is run on automatic differentiation or scientific machine learning. So there are a lot of different buzzwords for that, but we see this convergence being accelerated. 4 years ago, however, there haven't been many libraries in this space, so we started to develop our own, and we called it Neuromancer. We have chosen PyTorch as our backend for user friendliness primarily. That's one of our requirements. How can we make things as simple as possible while adhering to certain conventions in existing libraries in engineering and operational research. So what you can see here is that we go from symbolic form of problem formulation. Here I have some non-convex constraint optimization problem with some nonlinear objective and constraints. And I want to parse this in computational graph in PyTorch, or you can call it physics for neural architecture. So for that, we are leveraging the variable abstraction that is a symbolic representation of our decision variables and problem parameters. This is the same set of abstractions that you would be familiar with in JUMP, CVXPy, or Casadi, or PyOmo when you're coming from operational research. We are using operator overload to allow very expressive command line interface. In principle, any PyTorch callable can be used not only with PyTorch tensors, but also with Neuromancer variable symbolic expressions. Under the hood, these are NN modules, which is the base class for the quote-unquote neural network architecture in PyTorch. So we are building these computational graphs that are fully differentiable, assuming that those expressions are mathematically differentiable. And now you can combine these symbolic engineering or domain specified expressions for your objectives and constraints on the top of machine learning models. So here I have multi-layer perceptron that is standard neural network architecture that we wrap in this node class that is kind of a symbolic wrapper that we provide what are the inputs and outputs in a symbolic space. And now we have trainable components with some constraints that we can optimize with a range of methods. The simplest one would be the penalty one, that you are optimizing the trainable parameters of your mapping, which will be the neural network, to satisfy the objectives and constraints. And surprisingly, these layers of abstractions is very powerful. We have been really redesigning it several times to find minimum numbers of abstractions to cover wide range of scientific machine learning categories, whether it is learning to optimize, which I want to talk about next, or learning to control, or system identification of dynamic system, or physically informed neural networks. I want to show you that really we are using exactly the same API for all of these cases. The learning to optimize is a concept of warm starting constraint optimizations, where you are replacing iterative solver with neural network that is trained either on imitation learning or using gradients for your objective functions and constraints to update the parameters of the neural network. And once trained, then the neural network will replace the iterative solver. So you can really think of it as solving a distribution of problems as one instance at a time. So what is the advantage of it? That you can get orders of magnitude acceleration. So here is a very simple demonstration on 2D example when I have two decision variables, and I want to find minimum of this function that is given in contours, while satisfying certain feasibility constraints given in this half donut feasibility region. And the green one is the solution obtained by iterative solver interior point. And the red one is the solution obtained by differentiating the constraint optimization problem, constraints and objectives, and training neural network as a warm starter. Well, you can see that in every frame is a new problem. For neural network, the only thing that needs to be done at the inference time is just to evaluating the expression. While for the numerical solver, you need to solve new problem and again from scratch. So that's where the computational gains are obtained, because you're offloading the computations offline rather than online. So there are a lot of advantages when you want to deploy this on the edge, or when you want to explore a large number of scenarios in this way. The problem, though, very often we are relaxing constraints in physics-informed machine learning through residuals and penalizing soft constraint violations. That can be issue with safety critical systems. So there is a lot of research on feasibility restoration or safety filters that will be correcting these violations. So here is an example where neural network is poorly trained and is outside of the feasible region, and that feasibility restoration layer, which in this case is a projected gradient method, is making steps towards that feasibility domain. So there are a lot of new methods that are being published in the community that systematically combine neural network architectures with optimization solvers. Another area of capability that we are heavily interested in is nonlinear system identification, or learning to model dynamical systems specifically. So we are having different abstractions. Physics-informed neural networks is one of them, where you are having soft constraints in loss functions to satisfy ODs or PDs. Neural differential equations, very nice functional approximator for continuous time dynamic systems. Network dynamic systems that you can think again as a continuous time graph neural networks. And what is also important for our engineering applications is we have ability to build component-based models. That's something that you would be familiar with MATLAB Simulink, that each of the component represents different part of the system that may have different physics, and you treat it as an input-output model. Why we want to have that? Because very often in engineering applications like power systems or buildings or robotics, we know some parts of the physics very well. So we would like to have white box model there, physical equations that are numerically behaving nicely. But other parts of the systems are either partially unknown or fully unknown, or have poorly defined gradients. So we would like to approximate them with neural networks or some kind of gray box models. So we want to have the capability of assembling heterogeneous components in a single modeling abstraction. And once we have accurate predictions of the system dynamics, then we can close the loop with control policies and train control based on these differentiable system models and parameterized objective functions that we know from control. So people who are coming from deep reinforcement learning, you can think of this as offline model-based reinforcement learning, where the critic, that is typically a neural network in actor-critic methods, is replaced by differentiable model and differentiable optimal control objective. So that's the fully model-based approach that allows you to compute sensitivities directly on the system dynamics. And you can use it on all range of control problems, stabilizing unstable systems, or trajectory optimization, obstacle avoidance. We have applied this to many application areas, from buildings to power systems to robotics, with great success. Of course, some applications are more complicated than others, and it all depends on the numerical conditioning of your system dynamics. All what I'm talking about is differentiable programming-based approach, which means that you need to have differentiability of all of your models, so the gradients are well defined. So that's a very high-level overview of the capabilities and the API. What I want to do next is to go through our GitHub repository and do some kind of hands-on coding examples. And here, please feel free to reach out with questions. I don't think I will see the chat or raised hands, but feel free to interrupt me if there is question to clarify. So right now I am at our GitHub webpage, where you can learn a little bit more about the library. So I mentioned that we are a library for learning to optimize, learning to model dynamic system, learning to control, and physics-informed neural networks. And we have been really thinking hard, how are we going to unify the user experience across these, what is originally different modalities of scientific machine learning. So here I am going to show you first example of the learning to optimize, a constraint optimization problem. think I should have it open over here. Where for those of you who are coming from operational research, this will be very intuitive. For those of you who are coming from different domains, we have mathematical problem formulation of this parametric optimization problem, where I have some objective function, in general can be nonlinear, that has decision variables. X, we call it primal decision variables because they're also duals. And we have parameters theta, and these can be weighting factors in objective functions or boundary conditions in your inequalities over here. So it's a very generic problem formulation. In typical operational research approaches, you would implement this in algebraic modeling languages and use specific solver to solve each problem individually. So for distribution of parameters, let's say you have 1,000 samples, you need to solve 1,000 problems. Here, we are going to train neural network that will map this distribution of parameters into the distribution of solutions of this problem. So on the abstract way, that's the underlying idea. Here I have specific problem formulation that I will be solving in this particular Jupyter notebook, where I have this nonlinear objective function that's a typical Rosenbrock test problem, subject to some non-convex constraints. So it's small dimensional, but non-convex problem, which is the harder family of problems. So I need to start with sampling the parametric space, because these are sampling-based methods, learning to optimize. We are going to have a distribution of problem parameters that, in this case, they are sampled as uniform distributions, but it's really up to the user to choose the appropriate distribution for their problem. And for people who are familiar with PyTorch, you would typically have your data set of tensors that you would load in PyTorch data loaders and have neural network architecture and having tensor to tensor map. Because we are working on symbolic expressions, we also work with dictionaries as our data sets. So our keys are the variable names. In this case, these are the two parameters, A and P. So A will be this scaling factor in one term of my objective function, and P would be scaling factor in my constraints. And I'm going to sample them. So I will generate some distribution of torch tensors. And everything what follows is, this is standard PyTorch data loader. So everyone who is familiar with PyTorch should be familiar with this. Like you can choose mini batching, full batch, all kinds of like hyperparameters, how to actually sample these during training. So I'm going to skip all of these details because that's not specific to our library. I just want to give you a little bit of intuition behind the sampling. So here I have these two parameters, A and P, and I have some training data that are the blue dots that are sufficiently covering this parametric space. And I have some red dots, red samples that will be in a test case. What we are assuming, there is no distribution shift, so we are actually testing on the same training distribution. So now I want to define some function approximator that will give me a surrogate for this solution of the parametric optimization problem. So that mathematically is a simple mapping from the parametric space to the solution space. And technically, you can choose really any function approximator, whether it is a linear or fully connected neural network or residual network. For more complicated use cases, you may want to use graph neural networks, all kinds of, basically anything you can implement in PyTorch, you can use with Neuromancer library, because only thing what we are doing, we are taking the callable and making a wrapper with this node class. So that's one of our unique abstractions that will allow you to specify what are the symbolic inputs and what are the symbolic outputs of this callable. And how we are doing that? Well, we are leveraging the positional argument. So if we know that this multilayer perceptron has two positional arguments, which in these implementation we have star arcs, which have arbitrary number of arguments on inputs. We provide that many variable names on its inputs. And if we know that it has one output, then we provide that symbolic name to the output. And I see there are some questions in the chat, maybe. Yes, I will share the links. Oh yeah, someone is already sharing. Perfect. Yeah, feel free to follow the Jupyter notebooks. This is the part 1 on parametric programming, or so-called learning to optimize. Okay, so now I have the symbolic wrapper. Next step, I want to introduce some kind of constraints and objectives. So I'm going to instantiate the variable. That is our primary abstractions for objective and constraints expressions. And notice that this variable has the same name than the output of this neural network. So it will basically act as a pointer to the output of the neural net. And everything is on the symbolic layer right now. So the advantage is that the expression can be evaluated with tensors of different shapes. And during training, we assume that the tensors will be in 2-dimensional shapes, where the first dimension will be your batch size, how many samples in single batch you have, and the second dimension will be the dimension of the decision variable itself. I know that this is a 2-dimensional problem. So just for ease of modeling, I can slice it based on indexing. So we really support wide range of expressions. So they are like either standard algebraic expressions or slicing or any PyTorch callable, and any PyTorch function would work and create this symbolic expression. On the top of which we can either call the minimize method that will instantiate the objective term for a physics-informed loss function, or instantiate constraints by simple comparator operators. And to give you intuition behind like these expressions. So here I'm calling the show method of this f, which is basically composite expression of this algebraic expression. And it's a symbolic computation graph, really, what you see in here. So you have, you can analyze it if it helps you like this visual understanding, but under the hood, it's still NN module. It's still PyTorch architecture. So this allows you to basically construct 3 fundamental building blocks of any physical information machine learning model up to this point. What are the objective function terms? What are the constraints you want to impose on your machine learning model architecture? So these are the 3 fundamental components besides the training data. There are different ways how to handle the constraints and objectives. The most simplest one is to use penalty method, where you're just penalizing the violations of these constraints. There are a little bit more advanced or involved methods like barrier penalty methods or augmented Lagrangian that we have implemented in library. And there is way more in the research literature that you can implement yourself. Basically, they are providing you with aggregating the information from the objectives and constraints and giving you scalar valued signal that you can backpropagate through the computation graph to update the trainable parameters in your trainable machine learning architectures. So for that, we are aggregating it in a problem. That's our primary class for putting all of these pieces together. And visually, you can show this computation graph on very high level. We are sampling the data in a data set. So these are the problem parameters. I'm taking the neural network to map these problem parameters in the decision variables that are being used to evaluate the constraints and objective function terms that are aggregated in loss function aggregator like penalty methods or augmented Lagrangian to allow you to have a signal for gradient-based optimization. So you take the gradient for back propagating this through the architecture. So you notice there is no backward at this stage. For training, we have this. You could call backward yourself. You can really design your own training loop. There is a lot of flexibility in the library. If you don't want to do that, we have this trainer, which is again helper class to just provide you with few hyperparameters to tune, like learning rate, number of epochs, and early stopping. Select your optimizer, which is standard stochastic gradient descent from PyTorch, to train your problem on a given data set. And that's really it. Then you do trainer.train and you wait a couple of epochs, and you should see the convergence to the solution. If everything is well posed, then you have a reasonable amount of training data and there is no distribution shift, then this is a solution to non-convex nonlinear optimization problem as a parametric solution. If I would change my parametric point, let's say I change it a little bit like this, change the shape of constraints and change the objective function shape. Now I'm computing the solution with interior point using Casadi framework for benchmarking. And I should plot new solution. And you see like the constraints expanded, the objective function a little bit twisted, but you are getting very good approximation with this neural network close to the interior point solution. But the main advantage is somewhere here, if it was calculated, that you get solution speed up factor like orders of magnitude. Like it's really like a very good warm starter for optimization solvers by using this method. See, there are some questions. Okay, no questions. Let me go back to the library, show you some other example. And probably it would be physics-informed neural network for people in applied math background. There are a lot of methods for solving partial differential equations, finite element, finite volume methods. One of the methods are collocation-based methods. And physics-informed neural networks are really in that category, where you are sampling the domain of your partial differential equation using neural network as your basis to give you estimate of the solution of your partial differential equation, and then you are actually evaluating the PDE and penalizing the residuals of violating the PDE constraints in your loss function. So if you have seen the computation graph on learning to optimize, is exactly the same than a PDE solution here in PINS, because the underlying idea is the same. So I hope the similarities are visible right now. I want to quickly skim through this example, where in PINS you typically assume that you have diffusion equation or any PDE at hand. So it's model-based approach. You're having physics, but you want to get the solution. And you don't want to use finite element or finite volume method for some reason. You want to sample the collocation point in your spatial temporal coordinates. So here is the example of the sampling of two-dimensional PDE, where you have one spatial dimension and one temporal dimension. These blue points are the collocation points that will be used for training, and you may have some supervisory signals for your initial and boundary conditions. These are the red points. So that's treated as a labeled data set, and this one, the collocation point, is treated as a really unlabeled data set for which you need to evaluate the violations in the PD constraints. And again, I'm using the same type of data set. I'm using dictionary data set to define my spatial and temporal coordinate variable. These are PyTorch tensors that have been sampled. However you sample it, really doesn't really matter. What matters is that this is torch tensor. And I'm using PyTorch data loader, standard stuff, to do mini batching for training this neural network that will be mapping spatial and temporal coordinates in my PD solution. And I'm using, again, multi-layer perceptron, the same neural network class that I used in previous example. I'm just changing the activation functions from ReLUs to TAN-H, and I'm using node class to wrap it again in a symbolic layer. So it will be mapping spatial temporal coordinates in the PD solution. But the next steps, okay, I need to have this pin layer, physics informed neural network. For that, I need to compute gradients here, first and second order gradient of my neural network, because the neural network will give me the solution of the PD, and the PD is this, this expression. Well, for that, I'm going to leverage our variable classes that will allow me to do it on a symbolic layer. So I have my PD solution, that's what I had, and spatial temporal domain. And then I'm using .grad method, which under the hood is calling automatic differentiation of PyTorch to create the gradients in a forward pass, but we still treat it as a symbolic expression. So this dy dt, dy dx, and second derivative of y with respect to spatial coordinates, these are all symbolic expressions that allow you to really build command line expressions of your pin layers. And you see, it's fairly complex expression that combines constants and PyTorch callables together with our variable symbolic classes, instantiated classes. And what is being instantiated is a new variable that is NN module. So you can evaluate it with dictionary datasets, as I'm doing over here. Here I'm checking the shapes, but the nice thing about it is because it's the symbolic, you can change the shapes in your datasets. It's not checking the shapes of your input data as a hard requirement. So it gives you a lot of flexibility when evaluating or training these physics informed neural networks. And then if you visualize this pin layer, okay, this is very messy because there are a bunch of constants and expressions. So you could probably arrange it a little bit nicer, but it, again, gives you the visual intuition behind the computational graph that is that pin layer that is sitting on the top of neural network abstraction. And next, we want to define our objective terms and constraints. So the crux of the pins is collocation point method, where you want to minimize the residuals of violating this pin layer. Oops. Okay, so that's this one. So you just want to drive this towards zero, because when this is converging to zero, you know that the physics is being satisfied. Then you may have some initial and boundary conditions that may come with some labeled data. So this is standard mean square error loss with these residuals. And you can add a bunch of other constraints. So here are penalties on violating the boundedness of the domain of your neural network solution to the PDE. Because in this particular case, we know the domain needs to be between minus and 1. We can really impose that as additional constraints. And then you put everything together. In more complicated practical applications, you can have dozens of objective function terms. So That's also one of the tricky parts. If they are not numerically well posed, you really need to balance them with some kind of scaling factors. In this case, this is a textbook example. We don't need to really rescale any of these terms. And this is how they look in the code. So I have these collocation points where my pin layer needs to be equal to 0 because that's the satisfying PD constraints, where I have initial and boundary conditions. So they need to be equal to some supervisory signal that is coming from the data set. And I'm saying that the solution of the PD needs to be in some bounds, that -1, 1. And what I'm showing over here, this is not the exponentiation. This is expression for choosing the norm. So if I wouldn't use any, this would be one norm, and this would be two norms. So this is a little bit like technical detail, how under the hood we are parsing this expression for instantiating these objective function terms and constraints, but you have full degrees of freedom to really define your own expressions. These are only like placeholders or expressions that are commonly used for user friendliness. And if you remember, I used penalty method to construct objectives and constraints in trainable loss function for learning to optimize, and I'm doing exactly the same for pins over here. I have a list of objectives, list of constraints, and then I'm constructing the problem that will train this PDE neural network solution on this loss function, using exactly the same API for trainer with stochastic gradient descent, and then after converging, you should see some solution of the PDE that has been trained on the spatial temporal domain, and you can compare it with the true solution obtained by some other numerical solver. And then you can visualize the error compared to these solutions. So what I want to highlight here is that we are using exactly the same API for learning to optimize and pins, which we believe can be enhancing the productivity and understanding of these methods for diverse communities. Is there any question while I'm switching to another example?
So we do have one question. Excuse me. We do have one question from Ahmad, who asks, is it possible to conduct pin-based framework for inverse mapping using the trained forward pin?
Yes, it is possible. And here, the part 3 is an inverse problem with parameter estimation. So yeah, it is possible, but there you are also working with some kind of training data. So we don't have time to go through this one, but I would encourage you to look at the part 3. And we have a lot of references to publications that are using pins for parameter estimations, or they also call it hidden physics networks. There is a lot of wonderful work in the community for solving inverse problems with scientific machine learning tools.
Thank you.
One of the related inverse problems, maybe I can show you this parameter estimation of the ODE. That would be this part 2 example. Should have it already preloaded. Restart session. Run all. So this is neural ODE, black box function approximator, where I want to approximate this vector field given the time series data from different initial conditions. And I'm going to use neural network to approximate the right-hand side of this. So what I'm doing right now, I'm just running the notebook. You can run it yourself. You don't need to like install any library locally. You can just pip install in this window. So what I will be doing here is this wonderful oscillator. It's a canonical ordinary differential equation that is being used as a training in many textbooks and system identification libraries. So for that, I have some implementation in SciPy that I can simulate and generate the data. It's taking a while while installing this. Okay, I don't want to wait. I just want to show you the results. Yeah, the installation part can take up to like 2-3 minutes. And I don't want to waste everyone's time with that. Okay, so this is my training data. Measurements of my two states in van der Pol. So it's the periodic orbit. This is the attractor. And I want to sample this trajectory. So typically what we are doing, we are cutting the trajectory into smaller chunks with specified prediction horizon. This capital N. And it gives us this M number of batches. For that, I have this helper function that help me to create those, but you don't need to worry about details. What I want to highlight, I'm using exactly the same dataset dictionary where I have symbolic expressions of my states and initial conditions, and I'm using the same PyTorch data loaders than before. So exactly the same API. And now, instead of mapping problem parameters to the solutions of PDE or solutions of the constraint optimization problems, I'm going to map the current state measurements into the derivatives of my ODE. So this differential equation. So it's continuous time model. And I assume I don't know nothing about the right-hand side. So I am using some kind of function approximator. In this case, again, multi-layer perceptron. You could use recurrent neural network, ResNet, whatever, or more fancier approaches like input convex neural network. We have very extensive library of useful neural architectures that we have been using in our applications. So you can just go and check it yourself. Here I'm using the simplest one for didactical reasons. And this is a tensor to tensor map that will give me the gradients of this derivatives of this vector. But in order to train it, I need to discretize it. And for that, we are using solvers of ordinary differential equations. So that's this expression over here. I'm solving the continuous time model to give me the next time step solution. And it really depends on what solvers are using and what step size did you choose to obtain different accuracy. But because we are implementing this in a differentiable programming library, we need to have gradients not only of the continuous time model, but we need to be able to compute the sensitivities of this discretized solution, which means propagating gradients through the ordinary differential equation solver. There are two ways how to do that. You could either use backpropagation through time, which has been used extensively in recurrent neural networks. It's very simple. You're just unrolling the operations of your ODE solver, like Runge-Kutta or Euler integrator, and you're backpropagating the sensitivities computed with automatic differentiation through this computational graph. That's what you would do in recurrent neural nets. With continuous time models, you have the ability to employ so-called adjoint state method. And this has been introduced in this neural ordinary differential equation paper, that instead of unrolling the operations and backpropagating the sensitivities through the unrolled computational graph, you are introducing the second equation that is called adjoint equation and augmented states that are called adjoint states to compute the sensitivities backward in time. It's very neat theory. I encourage you to read the paper and go into more technical details if you are interested. How does it work? From the user perspective, all you need to know that we are supporting both approaches, backpropagation through time by unrolling an adjoint state method, and we have them implemented in our integrators. So here I'm using adjoint base solver for NODE. That is really like, this is a wrapper for original implementation of this neural ODE paper. I provide this neural network right-hand side of my ODE, the time step and the method I will be using for solving the ODE. This is Runge-Kutta 4. And now I have differentiable ODE layer that I can use in my physics-informed neural architecture, and I wrap it again symbolically in the node class. Here, xn is my variable name for state, so I'm going to map state to states. Yeah, this is mapping without any external inputs, but we have examples where you could have so-called controlled differential equations where you have some input control parameter, or they can be time dependent. So there is a lot of flexibility to design your own neural ODE. We have also examples where you do white box or gray box modeling. So this doesn't necessarily need to be neural network. This can be any expression really that is differentiable. And then we introduce a new abstraction that we call system to provide with rollouts. So here are n steps. That's basically number of steps I want to do forward time rollout. And you can think of it really as a symbolic recurrent neural network constructor that will construct this rollout on the architectures in the list of nodes. More complicated examples, you can do even ensemble of models or more, and they can be constructed as arbitrary cyclic and acyclic computational graphs. So something I will show you in a control example, how I will be using this for having control policy and system model. And there are a lot of degrees of freedom for constructing this for yourself.
Jans, I'm sorry to interrupt you. I'm conscious of the time. We have 5 minutes left. I will have a few questions in the chat if that's all right.
Oh, perfect. Yeah, so I was running a little bit into some details, but let me just finish this. That all I want to show you that the API is exactly the same than what I was using previous example, solving this system identification problem, given the time series data, using exactly the same loss function and problem constructor that can give you system identification capabilities, and then you can do rollout on these dynamical systems. And the last example that I should have somewhere here is control. I have some ODE that I want to control. So I close the loop with the control policy. So this is like the conceptual diagram where I'll be sampling the parameters of the control and using it to train with the objective control objective function. So this is the parametric optimal control problem where I'm really putting together the pieces of the system identification that I showed before, the capability of doing rollouts on continuous time models or discrete time state space models with constraints like I was doing in learning to optimize and pins. So the same data sets as dictionaries, the same abstractions. Here I have system class that has control policy and model, and then doing rollout on this closed loop system that allows me to train this as a parametric solution. I think it was pre-trained. Every time I run this now, I should obtain new solution. So new reference means that if I would be doing it with classical approaches, I would need to recompute the optimization problem again. Here I have neural network that has learned the solution over a distribution of initial conditions that are starting over here, and these are at reference trajectories. So I want to stop over here and answer a couple of questions if we still have time.
Thank you. Yeah, we have time for 1 or 2 questions. We have some questions in the chat. So there's a question from Mati, who asks, are there ways to get the governing equations using SIND?
Great question. So we currently don't have example with SIND, but we have all the building blocks that you would require to build your own SIND system identification. If you want to have something very quick, there is a wonderful SIND library in Python that has been developed by University of Washington that if you are interested, I can send you the link.
Thank you. We have another question from Anmar. What about forced vibration cases where the PDE equal to applied force? And what about the weights of loss functions terms optimization? I'm not, Anmar, yeah. Sorry.
So I don't know, like specifically for the force vibration cases that we can take offline. We are providing a library that is expressive enough to do forward modeling, inverse modeling, system identification, learning to optimize, learning to control. So I believe that this case can be covered. And the weights of the loss function terms are typically use case specific. You really need to be careful with having your problem well posed. When you have variables that are in different scales, you need to balance them out. Currently, this is manual. We are looking at methods and tools how to automate or at least semi-automate, because this can be a lot of hindrance. It can be some manual tuning or grid search that you would need to employ very often.
Thank you. I'll go with a voted question. We apparently now have a voting system with. So great presentation. Can you comment on the difference between Neuromancer and other pin library platforms, such as NVIDIA Modulus? And also with this question, is there a way to interface Neuromancer with other CFD softwares, such as OpenFOAM for training?
Yeah, excellent questions again. NVIDIA Modulus and also like DeepXT library, they are wonderful tools. They are specifically tailored for solving PDEs. So pins and neural operators. Where our library is different is that we are providing the support for nonlinear system identification, control, and learning to optimize. So that's our scope is a little bit different. That's why we are less specifically focusing on PDEs, where if you want to go really like fancier modules, then Modulus would be a better choice for that. Interfacing with other libraries, well, if it is differentiable and you can create a wrapper for that, then yes, but it's a lot of work doing this like this way. How we are typically interfacing with high fidelity simulators, that they are sources of our training data for us. And then we learn surrogates and replace the need of differentiating through high fidelity simulators by having our scientific machine learning surrogate in the computational graph.
I'll squeeze in one last question. And if you can, in the meantime, share your contact details, perhaps it might be the best way to reply to the remaining questions. So yes. Ina asks, if you use the state space representation for dynamic systems in your formulation for systems for control.
Yes, and it's possible, and we already have examples. So I encourage everyone who is interested, go through the Jupyter notebooks, what we have. You may find like way more use cases that I was not able to present in 1 hour.
Brilliant. Thank you so much, Jan. Thanks for sharing your package with us. In the meantime, I'd like to say thank you again to everyone for joining. And I hope to see you soon in our next seminar. The seminar will also is recorded, so it will be uploaded to the seminar webpage and also the YouTube playlist that we have on the Alan Turing Institute channel. Of course, if it's okay with Jan, we will send you a more formal way of agreeing to this in the coming days.
Thank you very much, everyone.
Thank you. Thanks, everyone.
Thank you. Bye.
Great day. Bye-bye.